very good evening. I'm Rudana. So today our topic is about optimal economic dispatch using PowerWrld simulations. Here's our group members. Today I will explain how the PowerWrld simulation was carried out and how the results were analyzed for the base circuits under full loads and half load condition cases A to G. Here in the left you can see one base circuit, it's the case G, and I will show I have draw network. You will get all the operators here. With this I will draw the circuits, and then I will go to the tool, then run mode, play. Here it completes. You can see here it's this base circuits, it's of 275, and here there are thermal generator G1, G2, G3, 2 solar units, 4 loads and 6 transmissions, and here generator limits, cost efficiency and line limits were entered. And now I will close this, discuss other cases. Now here we can see it's the table, and these are the full loads. So first one we can see that both solar units set as 0, and so all the 1150 is supplied by thermal generators. And so we can see from the table that this is the worst and baseline case because the thermal generator operates at high outputs and fuel cost is maximum. Now comes the G. Here it's LSS1 supplies 100 MW directly to the system, so for which the G3 reduced to 305 and cost drops, and the here economic dispatch reduced to the most expensive generator first, proving solar directly replaced the thermal generator. Then it's C. Here it's the half output means 50, so solar support is reduced, for which G3 increases, cost increases, so we can say it's less solar, more thermal, higher cost. For D, here it's D, LSS2 is full output is 500, which is equal to LSS1, so general outputs are same as C, and which shows the same solar gives same economic effects regardless of which LSS supplies is the E. Here it's very small it has its SS2 25 MW, which means a very small solar contribution. G3 increases, cost rises, means when renewable penetrations is low, thermal dependency and cost increases. So for F, here we can see the maximum penetrations and G2 reduce, G3 reduce, lower cost, which means this is the best full load cases, maximum renewable and minimum cost. So for G, we can say it's a moderate solar contribution, and we have shown this in the simulations before. So which the cost lies between the non-solar and full solar cases, showing smooth economic dispatch response. Now comes the half load. So for half load is the first one, and this is a table. So the half load, the load is reduced but no solar support, so we can say it's the cost is much lower than full load due to reduced load. Then B, solar supplies a large fraction to the load and solar impact is strongest at low load. For C, we can say it's less solar, higher thermal generation by the table. And for D, equal solar power as case C, confirms consistency of economic dispatch. For E, its minimal cost supports, and for F, it's maximum solar at half field and it's lower cost, and we can say generators runs minimum limits, best half load cases. For G, it's moderate renewable penetrations and balanced and stable operation. You can say as solar penetration increases, the thermal generators and operating cost decreases. At half load, the same solar capacity has a stronger economic impact. Thank you. That's all from me.
Assalamualaikum and good day, Dr. Jasro. I am Fahadana Suha, and today I'll be presenting our group's finding on optimal economic dispatch using PowerWrld simulator. So as you can see in the diagram, several transmission lines, specifically TL1, TL3 and TL5, experience severe overloading. It's indicated by the red pie chart that exceed 100%. This overloading occurs because the system is trying to push more power from the generator to the loads than the physical lines could handle. So while the simulation successfully calculated all the economic dispatch costs, the physical constraints of the grid were violated. So this is an acceptable operating state that could cascading failures or blackouts. So therefore our primary task shifted from just finding the cheapest cost to finding the solution that is both cheap and safe. So to resolve this transmission violation, we proposed and simulated two distinct engineering solutions as presented by my friend just now. Solution 1 is by adding the new generator, and method 2 focus on adding a few transmissions line. As expected, installing a generator at bus 4 successfully eliminated all the transmission line violations. The circuit is now secure. We simulated reinforcing the grid by physically building new transmission lines parallel to the overloaded one. So TL1, TL3 and TL5. So this increased the total transfer capacity of the corridors. Let's analyze the result for the method 2, where we reinforce the grid by adding transmission line. So table 5.5 from our report showed that the data for the full load condition. So technically this method worked, the lines didn't overload. However, economically we can see a heavy reliance on the thermal generators. In the first row with no solar output, the cost peaks at roughly 50,500 ringgit per hour with a very high incremental cost of 55 ringgit per megawatt hour. However, as we introduce solar energy, moving down the table to the last row where both LSS1 and LSS2 are fully active, the cost drops significantly to 43,000 and 477. So this proves that renewable integration is essential for cost reduction, as it allows us to back down the expansion thermal generation from G1, G2 and G3. Next, we look to the 50% load condition in table 5.6. The contrast here is very striking because the demand is half to 575 megawatt. The total hourly cost drops from 25,000 to 29,000 range. But the most important number here is the incremental cost, which hovers around 23 ringgit to 26 ringgit. So this demonstrates a fundamental power system concept. When load is low, we only need to pay for the cheapest megawatt. Unless the full load scenario, we will pushing generators to their expensive limits. Here the system is running comfortably and efficiently. Now we're going to look at the financial reality of these two solutions. In this slide, I'm going to compare the total hourly operating cost for both methods under the worst case scenario, full load with zero solar output. So on the upside part, we have method 1 where we add the generator, and the cost is approximately 35,000 and 227 per hour. And on the downside, we have method 2 where we added the transmission lines, and the cost jumps significantly to 50,500 per hour. So why is there such a massive gap of over 15,000 every single hour? It comes down to efficiency. In method 2, adding transmission line is essentially just building a bigger pipe. So it solves the traffic jams on the line, but it forces to keep buying power from the same expensive remote generator G1, G2 and G3 to meet the heavy demand and losses over those long distance. So method 1 is much more smarter. By placing the generator directly at bus 4, the load center, we are generating electricity right where it was needed. So we don't just solve the traffic jam, we reduce the amount of power that needs to travel, which lowers losses and allow us to run the system much more efficiently. So this proves that solving the problem with steel and copper lines is far more expensive than solving it with a strategic generation. So to conclude our presentation, we have synthesized our finding into final recommendation. First, our simulation proved that renewable energy is not just green, it's economically vital. Across every scenario we ran, the integration of LSS or large-scale solar successfully offloaded the thermal generators, directly lowering the hourly running costs. However, the core of this assignment was solving the transmission violation. So when we compare our two solutions, the choice is clear. While method 2, adding the transmission lines technically fixed the grid, it was financially inefficient. It forces us to continue running expensive generators to push power through new costly infrastructure. Meanwhile, in method 1, by adding the generator at bus 4, on the other hand was the superior engineering solution. By generating power locally at the highest load point, we eliminate the transmission overloads. We reduce the hourly operating cost by over 15,000 ringgit compared to method 2. Therefore, based on both the lowest operational expenditure OPEX and the likely lower capital expenditure COPEX compared to building 3 new transmission lines, we conclude that method 1 is the optimal economic dispatch solution for this network. So thank you for listening. That's all from our group.